In this video, we're going to look at sets of complex numbers and what they look like if you try and draw them in the Argand diagram. We'll start with an easy one. So, what does this set look like? I'll explain what I've written in a minute. So this set notation here means the set of all Z in C. C stands for complex numbers. So in other words, this is the same as saying the set of all complex numbers Z such that the modulus of Z is equal to 1. Okay. Right, now the modulus of Z is the distance of Z from the origin. So, the set of all complex numbers Z for which modulus of Z is 1 is a set of all complex numbers at distance 1 from the origin. Well, that's quite easy to draw. We could do it in no time at all because, I mean, how do you get the set of points at distance 1 from the origin? Well, if you like, you get a pair of compasses and you put one end in the origin and the other end, open it to a distance 1 and then you draw all those points. Well, that's a circle. It's a circle with radius 1. So it goes through the point 1 there, minus 1 here, I up here, and minus I down there. So this is a circle centered on the origin 0 with radius 1. Okay, so I hope that was quite an easy starter. Right, let's try a different one. So, what about this instead? What about the set of all Z in C such that the argument of Z is less than pi over 4 but bigger than 0? So what does this one look like instead? Right, now the argument of a complex number is the angle that that complex number makes in the Argand diagram measured anti-clockwise upwards from the real axis. Okay, draw the diagram here and we'll try and work this out. Now the complex numbers with argument 0 are those where you don't have to go up at all from the real axis. In other words, they're all the numbers along this line going off to infinity in that direction. The complex numbers with argument pi over 4, those are the complex numbers that sit on this line, where that angle there is pi over 4, half of a right angle. So the complex number Z whose argument is bigger than 0, but less than pi over 4, well, they must be all the complex numbers where you've certainly gone round a little bit, but you haven't gone round this much. In other words, it's all the numbers that sit in this wedge here. And we're not actually including the ones along this line, because those ones do have argument 0. Okay, so that's what that one looks like. Here's another question. What about this set? Z in C such that the modulus of Z minus 1 is 2. Right, now this is a bit harder because here we haven't just got something easy like the modulus of Z equals 2. If we had that, then that would be easy. If this was the modulus of Z equals 2, that would just be a circle centered on the origin with radius 2. But it's not that simple. We now have Z minus 1 here. So what do we do? Well, the key to doing this one is to understand what happens if you have two complex numbers, Z and W, and you work out the modulus of Z minus W. So let's take two complex numbers. Z, which is A plus BI, and W, which is C plus DI. And And we're going to ask, what is the modulus of z minus w? Okay, well, we can do the calculation. Modulus of z minus w is the modulus of z, which is a plus bi, minus w, which is c plus di. Okay, collect up real parts, and we have a minus c, and collect up the imaginary parts, and we have b minus d, lots of the I. And of course, to take the modulus of any complex number, you just take the square root of the real part squared, and you add on the square root of the real part squared plus the imaginary part squared. This is the real part, this is the imaginary part, so we have the square root of a minus c squared plus b minus d squared. Now, this kind of expression may look familiar to you. If not, don't worry, we'll draw a picture. Let's suppose our z is somewhere up here and our w is somewhere down here, just to make the picture nice and easy. Now z was a plus bi, so there's an a there and a b there. W is c plus di, so c in the real direction, d in the imaginary direction. Now, there's a triangle which you form by joining z and w and filling in like that. That's a right-angled triangle, of course. This distance here is a minus c, because you've got a along, but you start at c. This distance here is b minus d, so the hypotenuse here by Pythagoras is just the square root of a minus c squared plus b minus d squared, which is precisely this expression here. So, what we have here is the distance between z and w, because it's the length of this hypotenuse in our picture. So whenever you have two numbers, z and w, two complex numbers, and you do z minus w and then take the modulus, what you end up with is the distance between those 2 points in the Argand diagram. Right, so back to our problem, the one that we were trying to figure out. So this thing, z in c, such that modulus of z minus 1 is 2, well, we know what the modulus of z minus 1 is now in terms of pictures. This thing is the distance between z and the number 1. Here, w, if you like, is just 1. So this says the set of all complex numbers z for which the distance between z and 1 is 2. So again, I think we're in a good position to draw this now. Here's the number 1, and we're looking for all the points z whose distance from 1 is 2. Well, again, get your compass out, open it out to a distance 2, put one end on the number 1 here, and then you'll get as far as 3 in that direction and as far as minus 1 in the other direction. And overall, you'll have a circle. Okay, you could probably work out what these points are here. I won't bother doing that now, but it would be good to label those on. It's always good to label things on the diagram. But overall, this is a circle, radius 2, but this time centered on the number 1, the complex number 1. Right, okay. Let's do one more example, just to check we're getting somewhere. What about z in c such that the modulus of z minus 2i is the same as the modulus of z plus I. So what does this thing look like? Right. Now, we'll do the same approach as before. Modulus of z minus 2i, this is the distance of z from 2i. It's modulus of z minus w, where w is 2i. This thing isn't quite in the right form. It's not the modulus of z minus something, it's the modulus of z plus something. But two minuses make a plus, so this is equal to the modulus of z minus I. Now why is that useful? Well, now it is in the right form. We've got the modulus of z minus something, so this is the distance between z and minus I. Okay, so what do we have? Well, we're looking for the set of all complex numbers z whose distance from 2i is equal to the distance from minus I. Let's try and draw it. Here's the real axis, here's the imaginary axis. 2i is somewhere up here, minus I is somewhere here. Now I can think of one complex number that's halfway, or whose distance is the same from here as from here, and that's the point halfway between. Okay, so there's a distance 3 all the way, so we'll have to go 1.5 down from here. So that must be I over 2. There's one point that's whose distance from 2i is the same as the distance from minus I. And if you think about it, the other points will be all of those things along this horizontal line. Why? Well, think of a point over here. The distance from 2i is going to be the same as the distance from I. Similar triangles, if you like. Yeah, and you can see any point along this line, you'll take the same distance to get to 2i as to get to minus I. So we've got a name for this thing. This is the perpendicular bisector. Perpendicular bisector between, or of, some people say perpendicular bisector of the point 2i and the point minus I. So it's called the bisector because it's halfway between the two, and it's perpendicular because it crosses the line that joins these 2 points at right angles. Okay, so those are the kind of techniques you can use to draw sets of complex numbers. You really just need to break it down into the basic concepts of distances in the Argand diagram or angles in the Argand diagram, and then you can't go too far wrong.